I'm Sean Parent. I am a principal scientist at Adobe Systems out in California. I've been at Adobe now, depending on how you count, about 22 years. I started my career there on Photoshop, and now I'm actually back working on Photoshop again. But I did run a research team at the company for about 8 years with Alexander Stepanoff on the team. For people who know who Alex is, he's the person who created STL. This is one of my favorite talks that I give on runtime polymorphism, but with 5 people in the audience here. If you guys want to hear about something else, just raise your hand and I'll talk about anything. I'm here for you guys. So, a while ago, let's see, I guess it was about 3 years ago now, at the Going Native conference at Microsoft, I gave a talk called C++ Seasoning, and I got a lot of requests after that talk to write a book. So my agreement has been that as I get asked to do additional talks, I try to flesh out a chapter from the book. So this is kind of the outline of the book, and this talk fits in about here. It doesn't matter if you haven't seen the other talks. I'll give you the background information. This just gives you a little bit of background. Now, all of my talks have a goal. The goal for this talk is to write code without inheritance. The reason why I state the goals in the negative, they're non-prescriptive. Right? I'm not trying to tell you what to do instead, although I'll present some alternatives here, but I'm going to present the problems that inheritance causes, and it's as a goal, it's an open-ended issue. So it's like strive hard to not use inheritance, but if for the problem you're trying to solve, it's the best tool you've got in your toolbox, then use it. Right? So it's not a rule, it's not a guideline, it's a goal. So what is inheritance? Right? So inheritance is a mechanism to implement runtime polymorphism where one class is derived from another class, but overrides all or part of that implementation. Okay? Now, here we're talking about class inheritance. There's other forms of inheritance, there's protocol inheritance, but in this talk we're talking about class inheritance. A quick disclaimer, in my example code, to keep the code readable, I leave out header files, inline function, namespaces, things like that. They're just ignored for clarity. So I've got a little IDE here for my slides, so we can write main, and this will output hello world. That's the idea here. So we're going to develop a little library. In our library, we've got some object type, which for now is just an integer. Okay? And we've got a function that can draw our objects by just streaming out our integers. Okay? We've got a document type, which is just a vector of integers, vector of our objects. And we've got a draw function to draw our objects, right? So fairly simple. That's my library. Some client code might look like this. We create a document, we add 4 objects to it, and we draw the document. And that will output this. Okay? So, some quick guidelines here. Write all code as if it were a library, right? Right. Reuse of your code increases productivity for you and your entire team. And writing unit tests is simplified if things are factored out into a separate library. So what happens if we want our document, though, to hold any drawable object? How do we go about solving that? Right now it's just holding one type of object. Well, the traditional way is we say, okay, for any type of object, we'll make object be a base class. And it'll have a vtable under the hood, okay, that's going to point to a virtual destructor, and we're going to virtualize our draw function. Okay, and now our document can hold multiple objects, right? My class type T, some other type T, right? But I can't store them directly in my document because they're variable size now, right? The different instances of different types of my objects in my document are different sizes. So what I'm going to store in my document are pointers of some kind, right? So my library now looks like this, okay? So I've got a base class for my object type. I've got my virtual destructor, okay? I've got my document type. To manage the memory, I'm going to use a shared pointer, right? That's what most people do. Right there. And so my client code now, I can write a subclass and I can output my document, right? I can put in my own type right there and I can draw it. Okay? So everybody following the code, fairly simple. So how many people see the bug? Anybody? No. Nope, it's an override. I don't have to declare it virtual because it's in the base class. It's virtual. Yeah, it works. I can run it. But there's a bug. There's a bug right there. Okay? So what happens is I come along and I new my object. I call InPlaceBack to put this into my document. The document has to grow its size. Growing its size can fail. That would throw an exception. Okay, I already allocated my class. It's not yet held by a shared pointer, and it leaks. Okay, so there's a small bug right there. So that's why most people in the C++ community will tell you, never call new directly. Okay, just don't. Okay, instead call make shared. Okay. So this is actually also more efficient for another reason. If I call make shared, then make shared is going to allocate the reference count for that pointer along with the object in a single block, as opposed to putting the reference count in a separate block if I just nude the object. Okay, so I have two wins there. That's exception safe, and it saved me a little bit of memory and a little bit of time. Okay. But there's a deeper problem with this piece of code, right? What happens here is I change the semantics of what it means for copy and assignment and equality of my document. Okay? Before, when I had my document and it just contained integers, I could copy it. It copied all the contents. Now it's copying pointers to all the contents. So I've got shared data. Okay. So in C++ and in programming in general, we define an operation in terms of the operation's semantics. So assignment is a procedure taking two objects of the same type that makes the first object equal to the second without modifying the second. That's the definition of what assignment means. If I look at the structure I've created, I have shared pointers in my document now pointing to a single instance of T. And if I think of those as the individual types, right, I can copy my shared pointer. That obeys the rules for assignment. Okay, but what I fail to account to is the relationships, the arrows, that those pointers point to something. And so if I take those into account, then I have intersecting objects. Okay? Those intersecting objects can interfere with each other. So really, I have a single object that's all instances of the shared pointer and what they're pointing to. Okay? So the structure is still copyable and assignable, but we have to do it through other means. The shared structure also breaks our ability to reason about code, right? Anytime I'm reading a piece of code and I see a shared pointer, and if you're coming from a JavaScript world or a Java world or a .NET world, this drives me nuts in what I refer to as the reference semantic languages, right? Which is all of those languages. Every time I see an object, I do not know who else is sharing that object, right? So I don't know when I call a function what are other effects that function is going to have on the object that I'm hanging on to. So I always say a shared pointer is as good as a global variable, right? So we want to choose the same syntax to have the same semantics. That enables code reuse and avoids combinatorial interfaces. This is what the entire STL is built upon, is this principle. Okay? So if a type has a proper set of basis operations, right, then it can be adapted to an alternate set of basis operations regardless of the syntax. Right? So if I have the ability to copy an object, then I have the ability to map that copy into assignment or into a copy constructor. Right, now C++ has defined semantics for operations on built-in types, including assignment, copy, equality, and address of. Okay. Now, it's interesting. Copy constructors are actually things that I see abused the most. I actually had an engineer walk into my office one time and said, so I'm writing this class and I want to be able to copy the class. So what do I call the member function that does copy? And I said, well, that would be the copy constructor. And he said, no, I'm already using the copy constructor for something else. This is a horrible situation because the compiler understands the semantics of the copy constructor and the compiler can elide your copies. So if you're using your copy constructor to do something without copying, then you really don't know what's going on in your code. Okay. So, in the book Elements of Programming, we say this: there is a set of procedures whose inclusion in the computational basis of a type lets us place objects in data structures and use algorithms to copy objects from one data structure to another. We call types having such a basis regular, since their use guarantees regularity of behavior and therefore interoperability. Right? So a regular type where the regular operations are implemented with the standard names are said to have value semantics: copy, assignment, equality. Right? Those are our standard basis operations. When objects are referenced to indirectly through a shared reference or a pointer, the objects are said to have reference semantics. Right? So shared pointer is reference semantics. An object in JavaScript is reference semantics. An object in Java or in C# is reference semantics. Okay. The next deep problem with our code here when we went to the shared pointers is that call to draw on my class T are often indirected through virtual calls, including the destructor, even when it's not necessary. Okay. I'm always heap allocating my class T, and access to my class T must be synchronized. Now, if you're programming in Java, some of this the compiler is able to optimize around from you because the compiler actually understands reference semantics. So it's able to do things like devirtualization and move things into scoped memory if it understands your code. In C++, it cannot. The compiler does not understand reference semantics, and nor can it under the current rules of the language. So the compiler cannot avoid the heap allocation. Sometimes the compiler can devirtualize the calls, right? Another problem here: polymorphism is intrusive, right? The document that we created here now that holds our object T base class, I can no longer put in a simple integer, right? Before I could. So even if I have a draw function on my integer, right? My integer is a drawable thing, but it would have to inherit from object T. And that means that if I want to use somebody else's class from their library, I have to put some wrapper around their class to turn it into a drawable object, right? In large systems, this becomes a huge problem, right? What you start to see is every header file includes a ton of header files, and every object inherits from a whole bunch of things. And the problem stems from our use of the notion of the term polymorphic types, right? All of these problems. The requirements of a polymorphic type, by definition, comes from where you use the type okay? Not from the type itself, right? So an integer is not a polymorphic type, okay? My integer might be drawable, okay? What I'm saying is there is a piece of code within which I want to deal with a set of types, such as integer and my object t base class, and whatever else I create, okay, that share a particular attribute. So I want to handle those objects as if they were the same. That's what we mean by a polymorphic type. So when I use inheritance to represent that relationship, what I'm saying is I'm building the use of my objects into my objects. Okay? And what I want to do is separate the use of my objects from my objects themselves. So there are no polymorphic types, only polymorphic use of similar types. Exactly what I said. We're tightly coupling components. Inheritance implies variable size, which implies heap allocation. Heap allocation forces a further burden to manage the object lifetime, hence shared pointer, unique pointer, all of these things. Indirection heap allocation and virtualization end up impacting my performance. Object lifetime management leads to garbage collection or reference counting. This encourages shared ownership and the proliferation of incidental data structures. What's an incidental data structure? It's when I have a data structure within my code where I have no single object that points to it. So if I have two shared pointers within my code holding on to some element somewhere else, that is a data structure, but there is no collection of shared pointers that represents that. That's an incidental data structure. Shared ownership leads to synchronization issues, right? If I'm trying to share these things across threads, it breaks my ability to local reason. They're as good as a global variable, and further impacts performance. Which leads me to this line. Inheritance is the base class of evil. So let's do something instead. Let's take our library here, and let's start mutating it. Okay, this is back to the original where our object is just an int. Okay, so the first transformation we're going to do is we're going to wrap that int into a class. Okay, so all we did here is we've got our object t and int self down there at the bottom holds on to it. We're going to have a draw function up on top that just knows how to draw integers. Okay, and we'll declare a friend function for drawing our object type that just knows that in order to draw this object, you're really just going to draw the integer it contains. Okay, so all we did was we put a wrapper around the int. Okay, that was it. Okay, we're going to let the compiler supply our copy and assignment operators, which it's perfectly happy to do in this case. And that means that we can still write the same code, and it still outputs the same thing, right? Transformation number one. So by writing a class that behaves like a regular object, we can increase its reuse. Okay, so next transformation. Let's take our object now with our int, and let's heap allocate the int. Okay, so we're just going to add a level of indirection. We'll store it in a unique pointer. We'll use make unique so we don't have a memory management issue. Okay, so we're still just holding now, instead of holding an int, we're holding a pointer to an int. Simple enough. Okay, do your own memory management. Don't create garbage for your clients, right? All the management of this pointer is inside of our class. That's where we want it, right? Now, we do have to add our own copy constructor here now. We can't rely on the compilers, okay? So we'll add a copy constructor, and we make sure that it actually copies. Copied objects are equal and disjoint. That's what copy means. Okay, we're going to add an assignment operator. Okay, so we're going to write our assignment operator in terms of making a copy, okay, and then stealing the guts of that copy, right? We're moving it here. This is kind of a standard pattern. Even though it's just an integer, move is the same as copy for just that int. Oh, I'm sorry, that's not true, because we've got a unique pointer at this point. So we're moving the unique pointer over and stealing the guts from the copy. Okay, so assignment is consistent with copy. Generally, if I create an object and then assign to it, it's equivalent to if I copy construct it. Okay? So this assignment satisfies the strong exception guarantee. That's a nice property. What do I mean by that? I mean, if we throw in the middle of trying to make this copy, we end up leaving the object in the state it was in originally. Okay? Basic exception guarantee is that the object still satisfies its invariance, okay, but it's in an unknown state. That's a whole separate talk. Okay? Assignment, like all other operations, must satisfy the basic exception guarantee. And if you notice, we don't optimize for rare cases like self-assignment, right? Sometimes people will say, if this thing is really, if I'm assigning it to itself, right, because that can happen through a reference, then don't do anything, okay? So this would actually go ahead and make the additional copy. But self-assignment is incredibly rare, and so the check to see whether or not you're doing a self-assignment in your system is slowing down the 99.9999 case in favor of optimizing the 0.0001 case. So don't do things like that. Okay, so our code now, same code, still works. Right. So doing this kind of separation, sometimes you want to do it in code. It's referred to as a pimple pattern or a handle body idiom. Okay, this can be useful for separating the implementation of your class from the interface. So sometimes you can have a private implementation. Here our implementation is just an integer, but that could be some class sitting in a .cpp file, and I want to keep all those guts out of the header files. Right? Structuring my code this way, putting an extra level of indirection is one way to do that. Okay, let's take a look at something here. We're going to decorate our code just so it tells us when we're doing construction and when we're doing copies. Now here's a little piece of code. So what's going on here? We've got a function that constructs an object, assigns it the value 5, returns it as the result, okay? And then down here, we have object X, which we assign from function. Okay, so our assignment, remember, is written in terms of copy. So what is this going to print? Constructor only. Anybody else? So he's correct. In almost every compiler, this will print this. It's not guaranteed in the current standard, but it will be guaranteed in C++ 17. Okay. So right now, this is called a return value optimization, and the way it works is that because I'm constructing object X here, my function my object T, the result of a function, actually lives in the scope outside of that function. And so the compiler knows that if it's constructing a result and that result is going to be used to do the return, okay, that's a named value, that it can construct it directly in place in the object T. This is what I mean by the compiler understands what copy means, and so the compiler can elide copies. So if you have your copy constructor doing something else, you don't know what your code is doing because you don't know when the compiler is going to call it or not. Okay, so let's change our code just a little bit. We'll construct an object with X, and then we'll assign it from function. Question? Yes. That's correct. So, which we couldn't be because the result is a local variable. So, okay. So what will this print? Anybody? CTOR twice and then copy. Very good. So where'd that copy come from? The last line, right where we did assignment. The copy came from right here. We actually wrote that copy, right? The first statement in our assignment operator is make a copy. So that's our copy. Okay? Okay. So we're going to rewrite our assignment in this form. Okay. What we want to do is say, don't take our assignment in terms of a const reference. Take our assignment by value. That actually hoists that out of the scope. Okay? And then we'll just move it into place. Okay? The general guideline here is to pass sync arguments. What's a sync argument? A sync argument is an argument which is going to be stored or is going to be returned from the function that we're passing it to. Okay? So if we're taking something and we want to basically move it somewhere else or return it, which is a form of moving it somewhere else, we want to pass it by value. Okay? The argument to assignment is a sync argument. So now that will print CTOR. Okay? We got rid of the copy. Why? Because we lifted. Okay? So in our assignment, we lifted out the argument, and now the compiler is able to do return value optimization from the value coming out of there into the argument of X. Get moved into place. Okay. So now let's go back to our document like this, and we want to reserve, right, just so that we're not seeing copies from our document growing, and then we're going to reverse the document, right? And reverse is going to do pairwise swap all the way down. So what's this going to print? Anybody? So we're going to do 2 pairwise swaps. There we go. So we got our 4 constructors, copy, right? All of those copies are copy to a temporary and then copy across in our pairwise swap. Right? So the problem there, we didn't provide our own swap, and we didn't provide now a move constructor for the compiler. So what we want is a move constructor, right, which is the double ampersand there. So we're taking an R value reference, right, and R value is a temporary. Swap in C++ 11 and 14 is written in terms of moves. So with move, since we know that the value being passed to us is a temporary, or the users cast it to a temporary with a move expression, which is what move does, then we can just steal the guts of it. Now that implementation to just move all of our members is actually the default. So all we have to do is say this. Okay? So now C++ 11 and 14, this will get picked up by swap. And that will print that. Okay, so we got rid of all those copies. Now here's a tricky one. What does this thing print? Okay, all we did is we took our object T and we wrapped it into a struct. Okay, and so now our construction, we construct it with 0 and then we assign through our function there. Okay, so same code as before, it's just wrapped one level in a struct. Our copy's back. Okay, this one drives me nuts. This is because of what I consider a language defect. Okay, for the move assignment operator, a non-static data member, direct base with a type that does not have a move assignment operator and is not trivial. Okay, So the compiler will not provide a move assignment operator, okay, on our sum type t unless all of its members have a move assignment operator. Now, the reason why that's a flaw is if that sentence there said instead of saying does not have a move assignment operator, said is not move assignable, then our copy would go away. Okay? So, because our code is move assignable, it just doesn't have a move assignment operator, which has a very particular signature. So we can't quite get away with that. So instead, we need to put back our copy constructor and default our move assignment operator, which will just move all of our members, which is a unique pointer. So that's going to work fine. Okay. Okay, so we want to pass. So we're going to amend our rule here. We want to pass sync arguments by value and swap or move into place. A sync argument is in the argument contained or return for this function. The argument to assignment is a sync argument. However, because of a language defect, you must write a move assignment operator. Okay. Now, our copy constructor, now that we have a move assignment operator, we can actually shorten our copy constructor to that, which is make a copy, which is an R value, and assign it into place. Okay, so we fixed that. Okay, so returning objects from functions, passing read-only arguments, and passing R values as sync arguments do not require copy. Understanding this can greatly improve the efficiency of your application. Okay, so if you didn't know all of this, these are kind of important things to learn. So let's get rid of that. And what should we do next here? Okay. The observation here is that our constructors, before they were taking const int x, but constructors are frequently sync arguments. Okay? Or the arguments to constructors are frequently sync arguments. And so we're going to go ahead, even though they're just integers and it's going to copy, we're going to pass them by value and move them into place, just to follow our own rule. Okay. Now we want to make this polymorphic. So up till this point, we've only held integers. Now we want it to hold strings. So we can construct our object with a string. We'll do it the same way. But we can't store an int model anymore, right? So what we're going to store is a pointer to a concept, right? In this case, our concept is drawable object, right? So we want a concept for a drawable object. So our concept for a drawable object is just going to be a base class for our implementation here. Okay, so we've got a base class, which is our concept. It's got a defaulted destructor, and our string model and our int model inherit from it. Okay, we're going to virtualize draw on it. So there's our virtual draw function. Okay, and we're going to provide a base way to draw a string. Okay, so fairly simple set of transformations, but our code's getting a little messy and a little long. Oh, we also have to worry about copy, right? So before we could just copy our int model. Now we have to virtualize copy. Okay. So we'll go down here to our concept, and we'll add a virtual copy, and we will implement virtual copy for our string model and our int model. But now we can do this. We can put a string in here. And this will work. So we've got a little polymorphism. But we've got a pretty big class at this point. Right? But we didn't allow our polymorphism to complicate the client code. And we're working with integers and strings which don't inherit from anything. So that's pretty good so far. The polymorphism is an implementation detail, and that's where polymorphism should be. Okay, but we have a lot of redundant code here, right? So what can we do with redundant code like this, right? We've got two draw functions that are almost identical, right? Do we have a language facility to just write that once? Anybody? The template, right? So we're going to templatize our draw, and we're going to templatize our construction. Okay. Now down here, we have two model implementations, almost identical, one for strings and one for integers, right? Well, that could be a template, just a model. Okay. So now look what I can do. I can write my own class, and I can provide a draw function. I could also just make my class serialized to a standard stream, and it would pick up my default draw function. Okay, so I can provide a custom draw function, or I can just provide a stream out for it. And now I can store my class T inside of my document. Okay? My class T inherits from nothing. It's whatever I want it to be. Okay? It's called the runtime concept idiom. It allows polymorphism when is needed without inheritance. The client isn't burdened with interfaces, factories, or class delegations. Okay? So I can adapt anybody's third-party code. All I have to do is provide a draw method, a draw function, standalone function, and I can throw it in and use it with this type. Okay? In fact, since I started this whole thing, my document, which is a vector of my objects, itself, I have a draw function because I'm calling draw document cout, right there's the last line. We've been calling that all along. So I can put my document into my document. Okay? And that's going to work, right? And it's not going to explode because it recurses forever. It puts the document into the document at the state the document was in at the time that I copied it into the document. Okay? So now I can have a document that contains 0, hello, another document containing 0 and hello, end of that document, my class T, end of the second document. Okay. So we want to shift polymorphic use. We want to make sure we're using regular semantics for all of our operations. That way everything works with containers, promotes interoperability, and there's no performance penalty. This code is as efficient as the base class mechanism is. That's exactly what it is under the hood. Okay, so, but there's potential performance wins because I don't have to wrap integers into objects, okay, or strings into objects, or third-party library things into objects and lug those things around my system. Now let me flip to a demo here. So, mirror my display. So this is Photoshop for anybody who hasn't seen Photoshop or hasn't seen Photoshop in a while. I'm actually back on the Photoshop team. When I first joined Adobe like 22 years ago, I worked on Photoshop for a number of years, and now I'm working on Photoshop again. So this is a shot that I took of at the beach in California. Some people think the seagull looks like it only has one leg there, so let's fix that. There we go. So now the seagull doesn't look like it has one leg anymore. Let's do something horrible with this image, right? I wanted a bluer sky, so let's paint in some bluer sky. And magenta is my favorite color. So let's paint in some magenta there. Okay, So why am I doing this? It's certainly not to display my great artistic talent. But over here, I have open what's called the Photoshop History panel. Okay? And even if I went and did something like said, take this entire document and say, let's just revert it all the way back to where it was. Okay, my history panel is still there. And what does that mean? That means that I can back up through every step of this document all the way back to when I opened it. Okay, so up through Photoshop 4, Photoshop had undo, but it only had one level of undo. Okay, now during Photoshop 5, we said we want multiple level undo, but we had a problem, and that's Photoshop was written using something called Mac App, which is a framework that Apple used to ship, and it had these command objects, and the way it would work is a command object would implement a bunch of member functions for do it, undo it, redo it, commit it. That's the basic model. So you would write a command, you would implement those things, and then you would get undo. Well, the problem was over the initial Photoshop development is people were storing the data that they needed in order to undo, redo, okay, prior to commit, hanging out in fields of the document, right? Well, where would I put this? I would put that there. So if you did two commands back to back, the second command might clobber the undo history for the first command, okay? And this was kind of strewn throughout the code, right? Because you had to put the data someplace in order to implement redo. So where do you do it? You hang it off some member of the document. And this was a problem. The code base, even at that time, was big enough where it was like, how in the world do we even find all of these places? And one of my colleagues, Mark Hamburg, said, I have this great idea. Let's get rid of that model entirely. All we're going to have is do it. Just do it. And between each do it, we're just going to make a copy of the entire document, everything. Okay, now Photoshop can handle massive documents, right? Like, you know, we've worked with JPL to create documents that are the surface of Mars to a 1 meter resolution, like the entire surface of Mars to a 1 meter resolution as one Photoshop image. Okay, okay. And our model is just make a copy, make a copy. Okay. So that gives you undo, it gives you the ability to step in and out, okay? So, but it also gives you more, because I have this handy tool, where is my tool? It's right here, called my history brush. So I can come along here and say, well, I kind of liked a little more of the blue there, so I will anchor my history brush there and come down here and say, well, I'll just put back a little bit of that blue. Now I'm not, if you see, I'm not painting blue. I'm painting in the state the document was in when I put the blue there. Okay? And if I say, well, no, I want a little less blue, I can paint back in the document in its original state. Maybe I didn't want the blue over the seagull's head. Okay, so this feature came along for free because Photoshop already had a clone tool that could clone from one document to another document, and it could clone from one point within a document to another point within a document. And so if we have a whole stack of documents, right, that's all our history is a whole stack of documents, then I can clone from one document into another document. So what does this have to do with our talk? Well, let's take a look. Let me turn off my mirroring. Okay, so this is what Photoshop does, right? When we make a copy of the document, it's a very lightweight copy, right? Because most of the structure is actually shared. Okay, so when we lay down a paint stroke, the only thing that's new is the tiles of the image with the paint stroke, right? Photoshop busts the entire image into a whole bunch of relatively small tiles, and that lets us just modify portions of it. So let's write an undo here. Okay. So what we want is our history, which is a vector of documents. And we're going to add the following commands: commit, undo, and current, which just returns the top of that vector. Okay? So all commit does is does a pushback of our document state, pushback of back, that's actually legal C++, and undo, where we can do a pop back. Okay, so we're going to write that. Now let's go all the way back up here. We don't need to document our CTORs, but we're going to look at copies. And we're going to take this code, and we're going to change it. So we create a history state, and we do, right, which is, we take our current document, and we put in 0 and hello. Then we draw our current document, we'll draw a line, and then we'll commit that change into our history. And then we're going to take the now current document, we're going to put 42, world, put the document into itself, and put in my class, draw it, put a line, and then we're going to undo, which will be back to our commit state, and draw the document one more time. Okay? So that's what this is going to print. Construct our document, copy, copy, copy. Okay? And then we're going to display our document like that, and then we're going to put it back to the state it was in initially. Okay? So each of those copies come in because, of course, we're copying our document to put it back onto itself, and that's going to copy all the objects within the document. And if you haven't figured this out yet, I don't like copies. So what are we going to do? Well, this is where all of our copies are coming from. They're coming from our copy and assignment operator. And I don't like that. So get rid of it. Okay, which means we don't need to virtualize it. So get rid of that. But we do have to make a change here, right? Right now, our object would just be movable with a unique pointer. So let's put a shared pointer in there. Okay. But at the start of this talk, I told you about how evil shared pointers were. So let's fix that. It's a shared pointer to a const. No place in this piece of code do we actually modify this object, the internals of it. Right? And an observation is that for polymorphic use cases of objects, having mutable objects is the extreme, extreme exception where there is benefit for that. And there's a good reason why. So if I have a virtual function that's mutating my object, okay, then what I am doing one of two things. I'm either saying that my subclasses can provide a different implementation, okay, which that's very problematic because that's going to change the performance guarantees of that operation and potentially a bunch of other operations on my object. Or I'm saying that my subclasses want to observe when this thing is set, but they're not actually mutating it. So rather than having them override my mutating virtual functions, what I should do is provide an observer function where I will call them when I have changed things. Okay? So, what we're going to do is make shared like that. And now, we got rid of all of our copies. Okay, and the code still works, and the code still has value semantics. Okay, there's a side benefit here. If I wanted to come along and say, in the middle of some transaction, the user hits Command S, and I save this document, I can just peel off a copy of my document, right? I've got document there in my async lambda, bound to my current H. Let's just make a copy of this document. So I can peel off a copy of this document, throw it into a thread, and draw it from the thread. right? And if you saw I had to sleep for 3 seconds there, that's just so it didn't come over, and that's what this would print, okay? Which is the state of the document at the time that I said save it. Okay, there's no race conditions there. I'm good and clean. So this is thread safe as well. Okay, so compared to inheritance-based design, it's more flexible, it's non-intrusive, it's more efficient. The polymorphism is only paid for when needed, so which is a huge benefit. So I find if I look at most class hierarchies, people don't know. They just like making everything virtual, right? They're like, well, I needed this to be virtual in this one case, so it's virtual everywhere. Okay. It turns out that if you write code this way, that you'll find that you need actual polymorphic behavior in just a few set of cases, right? Instead of all over in your code base. It's less error prone. The clients don't have to worry about heap allocation. They don't have to worry about object lifetimes or ownerships. It's exception safe, and it's thread safe. So we created, think about what we did here. We created a little library where we have an object type that holds any drawable object, where drawable is defined as has a stream out operator or its own draw function. Okay, a document of those, a history state with undo and commit. And we did that in less than 2 slides worth of code. Okay. So as we increasingly move to heavily threaded systems using futures and reactive programming and task queues, value semantics becomes critical to avoid locking and to allow us to reason about code. Right? If you looked in my save, I didn't have any mutexes, I didn't have to lock my document, just peel off a copy and send it away. It's my hope that languages and libraries will evolve to make creating polymorphic types in this format easier. If you look at like the language Go has this built in. The language Swift has this built in, and I'll take some credit for influencing Swift. I gave this talk the first time over a decade ago at BoostCon, which was Dave Abrams' conference, which is now C++ Now. It was the keynote there, and Dave Abrams is one of the key designers on the Swift language. And so go watch his talk from WWDC, and you'll see it's very much a copy of this talk just cast into Swift. Right? Some thanks there to Alex Stepanov, Howard Hinnant, and Dave Abrams, who've all provided input into this. A link there to where you'll find my papers and presentations. Talks from this conference. Today's version of this talk isn't yet up, but it will be before this conference is over. And I cited Alex and Paul's book, Elements of Programming, a few times in this talk. So that's the actual reference for that book. So it's a good book, a difficult read if you haven't read it before. So any questions? What's that? Drawbacks. What are the drawbacks to this approach? So the drawbacks, it's a little difficult with this approach if you have the equivalent of multi-inheritance, where you have a polymorphic use case where you want to handle things that are kind of a variant. They either satisfy concept A or concept B. It can be difficult to encode things this way. There are some ways around it, but they tend to get so verbose that I usually say if you are really in that situation, probably multiple inheritance is the way to go. Another drawback, because this is non-intrusive, also means that it's not self-documenting. Right? So when I have my class type that doesn't inherit from anything, but yet, in order to use it correctly, it has to satisfy the requirements of drawable, right? So it's just got this standalone draw function. There's nothing in the code that tells you, hey, the reason why that function is there is so that this can interoperate in this other place, right? So there's a pro-con there. The plus side is I can just lift up my drawable object and drop it into another system that has different polymorphic requirements, and I don't have to carry some whole class hierarchy along with it. That's just extra baggage. It's a trade-off. Other than that, I don't really know of any. So other than it can be a little verbose to type, like I said, I'd like to see a little more reflection in the language to get rid of the boilerplate. But yeah. Yeah. Will it conflict? So the question there is, I have my draw. If a library implements their own draw, will it conflict? Potentially, this is one of the downsides of using ADL for name lookup, which is argument-dependent lookup, which we want to use in this case because we want to call draw and pick up the draw that they implement. So the idea there is choose your names carefully and know that they're a hook point, and sometimes that might mean manually prefixing your names, like, you know, my class underscore draw, whatever, or my library underscore draw, so that you're clear that I mean draw with this semantics. If it's a common name, that's probably a good thing to do. So that leads into a whole discussion of why I think, you know, ADL was the wrong solution to the problem it tries to solve, and a different thing. Any other questions? No. Any questions outside the talk? Okay, thanks. I'll be here the rest of the conference.